Hi guys, this is Dr. Blum. Today I'm going to review a problem that's based on the Chapter 13 material. It's an equilibrium problem and we're going to use the ICE table technique in order to solve the problem. The problem I'm presenting to you is 4 moles of hydrogen iodide placed in a 5-liter flask. I'm heating the materials in the flask to 500 Kelvin. The reaction we're looking at is 2 hydrogen iodide gas molecules is in equilibrium with hydrogen gas and iodine gas. The equilibrium constant for the reaction was given as 0.016. So let's first look at a picture of what we're dealing with. It's always good to sketch out your problem statements, even if it is just a very simple sketch like this one's going to be. So we have a flask, and it has some hydrogen iodine in it. It's 5 liters. These are my initial conditions. And after some time, we're going to have our flask. We added some heat to it. We heated it to 500 Kelvin. And now we're going to have our hydrogen iodide, hydrogen and iodide found. And the question at hand is how much of our different components are going to be in our flask when we reach equilibrium. To solve the problem, we're going to use the ICE table, and ICE stands for initial change in equilibrium. And we're going to put our different components across the top. So here's our hydrogen iodide, hydrogen, and then iodine. Our initial conditions. When we do ICE tables, we always have to do it in terms of molarity or concentration. So we have to calculate the moles per liter of our components. So in this case, I have 4 moles of hydrogen iodide in a 5-liter flask. So my concentration is 0.8 molar. My products at the beginning, since I only put hydrogen iodide in the flask, we can assume that we have 0 hydrogen and 0 iodine molecules. The next step is to look at this idea of our Q by evaluating our mass action expression, which is the same thing as our K expressions, but at this point we're not at equilibrium. We're at our initial conditions, which we're assuming is non-equilibrium. But we need to figure out which way our reaction is going to go, if it's going to go to the products or going to go to the reactants. So we're going to write out our Q expression here. So Q is the concentration of hydrogen times the concentration of iodine divided by the concentration of hydrogen iodine squared. Now that squared comes from the 2 in our balanced equation. So that's really important in understanding and solving these problems, is that we don't forget the squared from that problem. Once we evaluate our Q, so we can substitute our initial conditions into our Q expression, and we get Q is 0 times 0, hydrogen concentrations and iodine concentrations are both 0, divided by 0.8. And of course that's going to give us 0, which is less than K. Because of that, it's going to mean that if Q is less than K, then we have to form more products for our reaction to go to equilibrium. Now this is always going to be the case if I have no products at the beginning. The equilibrium will always shift toward the products. You don't always have to calculate Q in this case because Q will be 0, and it will always be less than K. You may have to calculate Q if you have initial concentrations of your products at the beginning of your reaction. Then you need to calculate Q to figure out which direction the reaction goes to, which direction. So since we're going toward the products, we're going to determine our change. So the hydrogen iodide is going to change It's going to be negative because we're going to react our reactant, so we're going to lose our hydrogen iodide, and it's going to change by -2. Again, that 2 is coming from the balanced equation times some number x. And then my hydrogen is then going to be positive x, and my iodine will also be positive x. From here, we can calculate our equilibrium conditions, which is simply going to be 0.8 minus 2x, x, and x. At this point, we want to go ahead and put these numbers from our equilibrium, or these expressions from our equilibrium calculation, into our K. At this point, we are going to call it K because we are at equilibrium. So our K expression is the same one we wrote before. Hydrogen iodine concentrations divided by the hydrogen iodide squared. And we can put in our expressions that we just looked at, and we just developed, and that gives us x times x divided by 0.8 minus 2x squared, and that is going to equal K, which is 0.016. So at this point, the goal is going to be to determine the value for x. And we can do that in a couple of different ways. We can do a lot of algebra and quadratic relationship here. This is going to be a quadratic equation to solve for x. But the first approach is what I recommend, is to look at this idea of the small x expression. The small x assumption. Which is essentially going to say 0.8 minus 2x is going to be approximately the same thing as 0.8. We're not saying that x is 0. We're just saying that if we have a small x, that x is negligible, so that if I subtract 0.8 minus a really, really small number, I'm still going to get 0.8 back. Making this assumption is going to make our algebra much easier. So in our expression, if we can ignore the minus 2x, we end up with the expression of x squared divided by 0.8 squared equals 0.016. Solving for x, we're going to get plus or minus 0.101 molar. And again here, we know the negative cannot be the correct root because I cannot have negative concentrations. So the x from this expression is going to be 0.101 molar. We're not done yet. We have to make sure that this is a valid assumption. And what we do with this is called the 5% rule. If x is less than 5% of my initial concentration, that little subscript 0 down there just means initial concentration, then I can assume that the small x assumption was valid. So if we check in our case, 0.101 divided by 0.8, that actually ends up being around 13%. So unfortunately, in this case, this is not a valid assumption. Does that mean everything that we did in this point is invalid? Absolutely not. It is a very good idea to go ahead and make the small x assumption to solve these problems quickly and give you an estimate of what the number is going to be, especially in a multiple choice situation. In a multiple choice situation, this may be obviously the best answer, or the answer that's closest to one of the choices. And that would allow you to more quickly solve the problem than if you wasted 15 minutes going through the quadratic formula in an exam situation. Obviously, we want to be able to accurately solve this type of problem, and we're going to have to do the quadratic formula to do that, and I'm going to do that in just a minute. But it is still a good idea to go through this exercise. In general, K should be 10 to the minus 3 order of magnitude or smaller to make this a valid assumption, but you do always have to check to make sure that is the case. So since we now know that we do have to go through the quadratic formula, let's go ahead and solve it in that way. We're going to once again write our K expression out. And then we can solve this for x, and we need to get it in the form of a quadratic equation. So x squared equals, when I simplify this out a bit, I end up getting the expression negative 0.936x minus 0.0512x plus 0.01024 equals 0. And yeah, it's going to take a fair amount of algebra to work out to this step. I would recommend that you do go through that exercise on your own just to brush up on your algebra skills. But it will work out to this form. Now we are of a form that can go into the quadratic formula. Our old friend, the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. If you are doing this for a homework problem, I recommend using an online quadratic solver, or use one of your graphing calculators that can usually solve the quadratic formula for you just by putting in a, b, and c, just for your time. But you should be comfortable with using the quadratic formula in case you run across something like this on an exam. So here we can solve, and you find out again that x is equal to either negative 0.35 molar or positive 0.08076 molar. Here again we can ignore the negative root because we do not have negative concentrations. So let's go ahead and ignore that, knowing that then that x is then going to equal 0.0808 molar. At this point we could be done with the problem, but it's always a good idea to go back and finish calculating what the final equilibrium concentrations are of all your species, and then going back into the K expression and double checking that you do get the initial value for K back. So let's rewrite out our ice table. And we have our initial 0.800 molar. Again, I'm just being lazy with sig figs to keep my tables clean and easier to read. My change, so it's minus 2x, which is going to be about negative 0.16, and I'm going to gain x for both hydrogen and iodine, 0.08 and positive 0.08 for the iodine. That leaves us with our equilibrium concentrations of 0.64, 0.08, and 0.08. Put that back into our K expression. That gives us 0.08 squared divided by 0.064 squared, which actually does come back and equal 0.016. And with that, we have solved the problem. So we know that everything works. It goes back into our K expression, and our answers make sense. Alright, so let me know if there are any additional questions, you have any other problems that you would like me to solve in this manner. The best advice I can give you is just practice these problems. These type of problems are going to follow us for the next few chapters as we talk about acid-base chemistry and solid equilibrium. It's going to always go back to this ice table concept, so it's very important that you get the concept of these tables down now back in chapter 13 before moving forward. Alright, I hope everybody continues to have a great week, and I will talk to you guys soon. Thanks.